Okay, section 10.1. Okay, this section has lots of vocabulary in it. So what I want to start off doing is grab a page of notes there. And I want it, like it says up here, I want you to drawing on the right, and it shows 5 lines or segments that intersect a circle. But I want you to use the picture to write your own definition of each of these. So I want you to write your own definition of chord, secant, tangent, radius, and diameter. And you're going to write this definition just by looking at that drawing on the right over there. So pause it right now, go through and do that, and then we'll talk about it together. So, if you look at this, here's the actual definitions our book gives. Oh, actually, I'm sorry, first, here's our learning goals for today. So we want to be able to identify special segments and lines with circles. That's what we just looked at. We want to be able to draw and identify common tangents. And we want to use properties of tangents. So by the time we're done with this video and you've gone through your homework on big ideas, we want to be able to do those 3 things. So here are the book definitions. I think all of us are familiar with the radius. A radius is a line segment, right? Segments have a start and end. So it's a line segment to go from the center to to a point on the circle. A chord is a segment whose endpoints are on the circle. So you see this chord up here outlined in green, right there. So there's an endpoint, there's an endpoint, they're both on the circle. Now look at the definition for a diameter. It says a diameter is a chord. Well, a diameter is a chord because, look at this diameter, the endpoints are on the circle. That's what makes it a chord, but it's a special kind of chord, and that's because it also passes through the center of the circle. I know you guys have all seen a radius and a diameter before. Maybe we're just defining it a little bit different. A secant line is really similar to a chord. The difference is, instead of being a line segment, it's a line. It keeps going both directions. So if you look down here, you have this, whoops, different color. If you look down here, we have this line. It doesn't stop. It keeps going both ways, but it does cross the circle 2 times. So you can kind of see how a chord and a secant are related to each other. A tangent line is a line. This is different than the tangent we just talked about in trig, right? But it's a line that just touches, it intersects the circle in exactly one spot, so it just touches that point right there. So if you see this point B right there, okay, that is called the point of tangency. That's where it touches it. It also says the tangent ray AB and the tangent segment AB are also called tangents. So even if I just look at half of it, so I just look at that, just that ray just going one direction, we still refer to that as a tangent. Or even if I have a line segment like this, if I go from A to B, just that line segment right there, we still refer to that as a tangent line, even if it's not we refer to the tangent segment or a tangent ray instead of a tangent line. There's a bunch of definitions. If you want to go change or add anything to those previous definitions that we had there, you can pause the screen real quick and go back and do that. They're really simple then. We're just going to define these different pieces. We want to tell, this is our first learning goal, right? We want to tell whether the line, ray, or segment can best be described as a radius, a chord, a diameter, a secant, or a tangent. So those are our 5 terms we want to know. Okay, so AC is the line segment right there. That line segment we know is a radius. Put that here. Phonologist vocabulary. AB is a chord. It goes all the way across, but it does pass through the center, so we're going to call it a diameter. It wouldn't be wrong to put a chord there also. DE, the ray DE. So the ray is just going that direction. We call that a tangent. And line AE, if you look at AE, it passes all the way through, so we refer to that one as a secant line. Now, just as a side note, instead of saying line AE, if I said segment AE, okay, so I'll do that in a different color. Segment AE starts at A and ends. Oh, I did that last problem. No, that we're good. If I said, so let's do that different, sorry. If I said that was segment AG, okay, so I start here and I end there. Instead of being a secant line now, that part of it we refer to as a chord. So we need to practice those, make sure you know all that terminology. I think the radius and diameter, of course, you guys have seen a lot before, but know what a tangent is, a secant is, and a chord is. So I kind of got ahead of myself. This is asking what that's described as AG. We just did that. So from A to G, we would say that's a chord. And then CB, so we're going from there to there. That would be a radius, right? Going from there. Okay. We're going to move past that. If you have two circles and they're in the same plane means they're on the same two-dimensional surface. Those two circles, really, three things can happen. The two circles can cross twice, so it looks like that. They can be tangent circles, so it looks like that. Okay. Or they can have no intersection at all. Now, if they don't have an intersection, there's actually two things that can happen. It can look like this, where they never intersect. It can also look like this, where one is inside of the other. They share the center point, like that. If that happens, we say they're concentric circles. What we're going to look at is a tangent line, a line that's tangent to both circles. So let me show you these definitions here. So we kind of already talked about most of this, right? We have right here, we have 2 points of intersection. We have 1 point of intersection, right, where they just touch in one spot. And again, we say that they are up here tangent circles, if that's the case. And that point right there is a point of tangency. Or we can have concentric circles. So circles can have common tangent lines, and that's what we're going to look at next is common tangent lines. Let me go back to this slide right here. So an example of that would be, is these two circles would have a common tangent right there. You know, that's the line that touches both circles in one spot. But that's not the only tangent line, right? We could also draw a common tangent right there, touches in two spots. We could also draw a tangent line that goes this way and touches just 1 point there and 1 point there. And we could draw one going this way. Okay, again, that touches there and touches there. Sorry, my lines aren't perfect. So those two circles actually end up having 4 common tangent lines. The two I did in blue are referred to as external tangent lines. The two I did in red are referred to as internal tangent lines. You can see that right here. We have internal tangent lines, right, and we have external tangent lines. Basically, this is what happens, is if I draw a line from the center of both circles, so from the center to there, to center to there, oops, kind of missed my point there, but the external tangent lines never cross that line, that line from the center to the center. The internal tangent lines do cross that line. So if you're ever not sure if it's external or internal, draw that line from the center to the center and you can find out. Okay, so this says tell how many common tangents the circles have and draw them. Use blue to indicate the common external tangent and red to do the common internal tangents. So the external would just go this way. There's an external, there's an external. The internal tangent lines, they're going to touch both circles, but they're going to go inside. So they're going to go in that direction and that direction. On B, the external, it has 2 again, right there, and across there. The internal tangent's a little bit different because they touch in that one spot. So your internal tangent line is going to be that line that goes exact right between the circles and just touches both of them right where the 2 circles touch. If you look at this last example, is C here, external tangent line, external tangent line. These do not have an internal tangent line. I can't draw any circle that goes. I can't draw a line that touches both circles once that goes between the 2 circles. Take just a second, see if you can draw these two. So if you pause it for just a second, and on your notes page there or whatever, draw your external and internal tangent lines. It will look like this: external, external, internal, internal. This one only has That external tangent line is touching right there. Number 5 doesn't have either. Okay, no internal tangents, no external tangents. Okay, a couple of theorems, and you want to write both of these down. So both of these will be one included in your notes. So again, if you want to pause it at some point here for a second while the screen is showing and write it down, you can. The first theorem says a tangent line to a circle theorem, and what it says, and you'll see on these it says in a plane, that is means in the same two-dimensional flat surface. Anyway, sorry, so we have in a plane, a line is tangent to a circle if and only if the line is perpendicular to the radius of the circle. So what that means is, if I take the point of tangency, which is P, and I draw the radius for the center, it will always be perpendicular to form that 90-degree angle right there. Okay, this if and only if means it goes both ways. So if we know that it's a tangent line, and we draw that line, it has to be perpendicular. The opposite is also true, the converse is also true. If I draw a line that touches, and then I know it's 90 degrees, then I know it's also a tangent line. So it goes both directions. Your second theorem is saying this, is if I have a point out here, this point S, and I draw the tangent segment, so this segment right there from S to R, and then from S to T, those two will always be equal to each other. Right, so it's tangent segments from a common external point R, congruent, they're equal to each other. So those are two theorems you want to know. By the way, this stuff we're going through right now is great for, I always think of this as ACT prep, because there's a lot of geometry on the ACT, and this is some of the stuff that you see on there. So as you work through this chapter 10, think about that. Think of that as ACT prep. So next year when you take the ACT. Okay, so you'll get this problem. This is asking, is ST tangent to circle P? So the question is that line right there tangent? And you can't just look at it and say, yeah, it looks like it or it doesn't look like it. We want to have evidence and or proof. So what I'm really asking is, if that is a tangent line right there, it has to be perpendicular to the radius right there. So we want to check. The question is it a right angle? So the way we tell that is use Pythagorean theorem, right? I take my two legs, 35 squared plus the other leg, 12 squared. And the question is, does that equal the hypotenuse squared? If it does, then it's a right angle, which means it is a tangent line. So if we check that, we got 35 squared plus 12 squared. That equals 1,369. 37 squared equals the same thing. So it checks off. So we would say, is it a tangent? Yes. And our evidence is right there. So this one says, same thing in the diagram, point B is a point of tangent. Oh, this is actually different, sorry. It tells us it's a point of tangency. And it wants us to find what is the radius equal to. So here's what we know. If it's a point of tangency, that's given to us right there. It tells us it is. That means that has to be a right angle. So that means I can use Pythagorean theorem to solve this. And this is a little bit tricky. My legs are, this is one leg, 80 feet, so 80 squared, plus my other leg, which is R squared, is equal to, I've got to figure out how long that whole thing is. The 50 is just the outside piece right there. So the entire thing would be 50 plus R, and I have to square that. So we've got to solve this equation to find this. So let's do that. I'm going to take 80 squared, find out what it's equal to. So 80 squared is 6,400 equals, now when I square this right here, remember, that is not just 50 squared plus R squared. You can go like this, 50 plus R times 50 plus R, and do the whole distributive property, and multiply it out that way. If you do, you end up with 50 times 50, or 50 squared, which is 2,500. You end up with, so 2,500 plus 50R plus 50R plus R squared. So you end up with 2,500 plus 100R plus R squared. And by the way, if you want a shortcut, all you have to do is you square the first term, you times the two together, so 50 times r is 50r, times it by 2, that gives you the 100r, and then you square the last r squared, that's going to give that. Oh, sorry, I forgot something back here. Okay, this was 80 squared plus r squared, so this should be 6,400 plus r squared. Okay, I'm just going to go through and solve this now. So I'm going to get the r squareds together, so I'm going to minus r squared over, minus r squared over. What ends up happening is those two just cancel out. That'll make it our life a little bit easier. 6,400 equals 2,500 plus 100r. Minus the 2,500 over minus 2,500. So now we end up with 6,400 minus 2,500, which is 3,900, equals 100r. Divide by 100. So r is equal to 39. If you're not sure if you've done it correctly, you can go back here and you can, plug in 39. So you go 80 squared plus 39 squared, plug in 39 for r right there, has to equal 39 plus 50, which is 89 squared. And you plug that in a calculator and double check it, just to make sure that it actually works. So 80 squared plus 39 squared equals 7,929. 89 squared equals the same thing, so we got it. So now there's our answer. R is equal to 39 right there. A little bit more work. Most of the work there is just solving the equation. The idea is, the concept is just this, is if it's a point of tangency, then it has to be a right angle. And if it's a right angle, we've got a right triangle, and I can use Pythagorean theorem to go through and solve that. Okay, here's a different one. This is really simple. It says RS is tangent to C, so it tells us RS is a tangent line. RT is tangent to C, so RT is a tangent line. So this is that second theorem. The second theorem said if you have two tangent lines from the same point, the same circle, that they're always congruent. Those have to be equal. So all I have to do is go 3x plus 4 equals 28. I solved that, I got my answer. So 3x equals 24, x is equal to 8. Okay, got my solution. Here are 3 examples. Take just a second and pause this real quick. I want you to work down through these 3 examples right here. Find your answer for all of them, and then unpause it, and I'll look for it real quick so you can double check it. Okay, so this first one says, is DE tangent? So to be tangent, well, the real question is that a right angle? That's what I'm trying to check. So I can check to see if it's a right angle by using Pythagorean theorem. This is a little bit tricky. It says this part is 2. That's not that entire side, right? The radius right there is 3, so that whole side would be 5. So it's 3 squared plus 4 squared equals 5 squared. That's the question. The answer is yes, that's the Pythagorean triple. So is it tangent? Yes. This one's the opposite. This one tells us that it is tangent. So we know it's a tangent line. So we know that's a right angle. And once we define the radius, so this could be similar to the other one. I'm going to take r squared, that side squared, plus 24 squared. And that has to equal that entire side squared. So that's r plus 18 squared. So this would be r squared plus, grab your calculator, plug in 24. 24 squared is 576. Over here on this side, you can go r plus 18 times r plus 18 and multiply it out. This is called squaring a binomial. It's got 2 terms. So you can multiply that whole thing out. Or we can do our shortcut, just square the first one, times the 2 together, the 18r, and times it by 2, 36r. And then square the last one. 18 squared is 324. Okay, now we solve it from there. I'm going to minus the r squared from both sides. It's gone. 576 equals 36r plus 324. minus 324 over, divide by 36, and that ought to give us our answer. So it comes out to be, it's 252 divided by 36, so the answer is 7. So that's what R would have to be here and here, if that's a tangent line. Okay, the last one says M and N are points of tangency, so we know these are points of tangency. It's coming from the same point, that means those have to be equal. Okay, so on this one, all I have to do, go x squared equals 9, solve that, so you take the square root of both sides, x equals plus or minus 3. The minus 3 doesn't make sense because it's talking about it. Actually, for a value of x, either one would work, so make sure you include both negative 3 and positive 3. And the reason why is if I square negative 3, it's 9, so you get 9 and 9. If I square 3, I get 9, so it's 9 and 9. So make sure you're careful if you square root both sides, make sure you include that plus or minus, if you have plus or minus 3. Okay, that's it for this section. Again, a lot of definitions there. So make sure you're familiar with all those. We'll use those throughout this chapter to go through and discuss other stuff. Thanks, guys.